Continuing with section 3.3, let's look at example 1b as another illustration of the long division process. So we have f of x equals x to the fourth minus 2x cubed minus 2x minus 1. We want to divide that by x squared plus 1. So let's get things set up. So our divisor is x squared plus 1. We're dividing that into x to the fourth minus 2x cubed. Now let's stop a moment. Notice that we go from 3 to 1. The powers of x go from 3 to 1. We skip 2. If you skip a power of x, you should leave a space for it, or what I would suggest is add it in as 0 times that power, the missing power of x. In this case, 0 times x squared. It is often necessary to include such a term, a missing term, when you do long division, or later when you do synthetic division. It's also important. Then minus 2x, then minus 1. And put our thing over the top. And then we ask, we look at x squared, and we ask, what do we need to multiply it by to get x to the fourth? That would be x squared, and that would be your first term in the quotient, x squared. Then we multiply x squared times x squared to get x to the fourth. X squared times 1, that's 1x squared. Notice where I'm going to put that. I'm going to put it below the 0x squared term so that I'm combining like powers of x, like terms. Then, as we did previously, we subtract x to the fourth minus x to the fourth. That's a cancellation. Minus 2x cubed minus 0 is still minus 2x cubed. So that just comes straight down. Okay, now be careful here. 0x squared minus 1x squared minus 1x squared. So it's not going to be 1x squared, it'll be minus 1x squared. And then let's just go ahead and bring down minus 2x as well. All right, now again looking at the first term in the divisor x squared, we'd like to multiply it by something to give us minus 2x cubed. That would have to be minus 2x. Minus 2x times x squared is minus 2x cubed. Minus 2x times 1 is minus 2x. I'm going to put that below the other x term, minus 2x, which happens to be identical. We're going to subtract. And again, if you want to think of this as adding the opposite, you can. But be careful because you're changing the signs from what you had originally. But notice that the first and last terms are going to cancel. The minus 1x squared will come down. So everything else cancels. The only other thing left to bring down is the minus 1 that's on the very end. So we have one more step. Very exciting, isn't it? We're going to multiply x squared by something to give us minus 1x squared. That would have to be minus 1 minus 1x squared, and then minus 1 multiplies the plus 1 in the divisor to give us minus 1. Again here, the terms are identical, so when we subtract, they completely cancel, and our remainder in this case is 0. So to summarize, the divisor is x squared plus 1. The quotient is x squared minus 2x minus 1, and the remainder is 0. So we can write f of x according to the division algorithm as d of x times q of x plus r of x, with d of x x squared plus 1, q of x x squared minus 2x minus 1, and r of x 0. Since r of x is 0, we really don't need to even bother writing it. And what we see is that we have factored f of x. We have factored f of x. So, by doing a division and getting a remainder of 0, we are able to factor polynomials. This is not the way you've been accustomed to factoring polynomials, but this is a legitimate way to do it. And in fact, sometimes it's the only way you can factor polynomials, is to perform a division and see if you can get a remainder of 0. I mention this to you now because this is something that we'll see as we continue through the chapter. So the process of polynomial division is intimately linked with the process of factoring polynomials. And factoring polynomials is intimately linked with solving polynomial equations. Now, very often we want to divide a polynomial by what we would call a linear factor, a first degree, not a factor, but a linear divisor, a first degree divisor. And when we want to do that, we can use a shortcut for long division, which is called synthetic division, which is much easier and less time consuming than performing a long division. But it has to be used only in cases where we are dividing by a linear divisor. So synthetic division is used for divisors of the form d of x equals x minus a, where a is a constant. For example, x minus 1. Or say x plus 3. In that case, a would be negative 3. It turns out that to divide by a linear divisor is often really what we need to do anyway in factoring polynomials and in solving equations. So to show the process how it works, it's actually quite simple. We're going to do the same problem that we did. Our very first long division problem was x squared minus 3x plus 11 divided by x minus 2. And we'll do this by synthetic division, and you'll be able to compare the results and see that it leads to the same conclusion. But the method is just a little bit different. It's more of a condensed version of long division. It does not require that we write down any variables, and it allows us to use addition rather than subtraction, which makes things much easier as well. What we would do is, looking at our divisor, we notice it has the form x minus a, x minus 2, with a equal to 2. So we want to determine what the value of a is for our particular divisor. I'll put that 2 here. We'll write the coefficients of f of x next to that in a row. That would be 1, negative 3, and 11. Then I'm going to put a little L-shaped thing here, like this. Leave a little space there. And then here's how it works. I'm going to start with 1, and I'm just going to bring it straight down. You don't have to draw all of this in. So it's going to come down there. Then the 1 will multiply the 2 in the upper left corner. 1 times 2 is 2. The 2 you put below the negative 3. Then in this column you'll add negative 3 plus 2, negative 1. Then you just repeat the process. You'll take negative 1 and you'll multiply that by the 2 in the upper left corner. Negative 1 times 2 is negative 2. That goes below the 11. Then we add 11 plus negative 2 is 9. When we get our final number in the bottom row, we usually partition it off like so, because there's a different interpretation for that number than for the other two numbers in the bottom row. The interpretation here is that the quotient comes from this part of the bottom row. This is q of x and the remainder comes from the last number, the 9. And instead of using r of x, with synthetic division, it will always be a constant remainder. So I'm just going to call that r. It's a constant remainder. So our q of x, okay, how do we interpret this? Well, the degree of f of x was 2. Whenever you do a synthetic division, the degree of the quotient is always 1 less than the degree of what you divided into originally. So that would mean q of x would have to be a first degree polynomial. And that means that we'd interpret this as 1x minus 1, or simply x minus 1. So x to the first minus 1. The remainder, of course, as I mentioned, is 9. If you look back now at example 1a, you'll see that's exactly what we obtained previously using a long division, but you can see that with synthetic division, you're going to obtain your result much more quickly. Now let's look at a few additional examples of synthetic division, expressing our results in the form divisor times quotient plus remainder. Here we have a third degree polynomial which we want to divide by a linear divisor x plus 1. Now we want to match x plus 1 up to x minus a. And in this case, a would have to be negative 1. So the value of a is going to be negative 1 in this case. And that determines the number that you're going to put in the upper left-hand corner when you set up the array for synthetic division. So basically there's a sign change that's required. This sign change is what allows us to use addition in determining the quotient and remainder rather than subtraction. Then we write the coefficients of f of x, 2, negative 3, 4, negative 1. Notice there are no missing powers of x in this case. So 2, negative 3, 4, negative 1. We don't have to write any x's. Put this L-shaped thing right here, leave some space. And then the procedure again is bring down the first term, or the first coefficient, multiply by the number here, the a. 2 times negative 1 is negative 2. Now add along the columns. Negative 3 plus negative 2, negative 5. Now repeat. Negative 5 times negative 1, positive 5. 4 plus 5 is 9. 9 times negative 1, negative 9. Add negative 1 and negative 9, negative 10. We'll split negative 10 off from the rest. And now we can see that our quotient, q of x, would be, okay, it comes from here, and it's a third degree polynomial that we divided into. So the quotient should have a degree 1 less than that. This should be second degree. 2x squared minus 5x plus 9. And then the negative 10 here is our remainder. R equals negative 10. Now writing f of x in the form divisor times quotient plus remainder, we can write f of x equals x plus 1, the divisor, times the quotient, 2x squared minus 5x plus 9, plus the remainder, plus negative 10, or simply minus 10. That's all I have time for in this video. We'll continue with part B in the next video.